Hello, my name is Silas Gross, and this is my submission for Lab 1 Physics. The purpose of this lab was to observe motion of an object, particularly a marker in this case, on a surface with little to no friction, and to prove Newton's first and second laws. An introduction to the key terms are Newton's first law of motion, where objects at rest tend to remain at rest, while objects in motion tend to continue moving in a straight line at a constant speed unless an outside force acts upon it. Newton's second law of motion shows that acceleration is equal to the net force on an object divided by its mass. We'll be using the momentum principle and using the tracker model and GlowScript computational model for this as well. Consideration of the key beliefs of this is that the normal force is equal and opposite to the force of gravity. This is just showing that there's no net force in the y direction and that the friction will be small enough to be ignored here, which shows that there's no net force in the x direction, which shows that the total net force is 0 and there will be no acceleration. Additionally, angular momentum will not be considered here, as although we are using a marker, which is a cylinder, we're only tracking the point mass of it, and therefore it doesn't matter quite as much. Some of the initial conditions of this were that movement was recorded after contact with the marker broke, therefore there was no extra acceleration recorded. This is because if we started recording the mass of the marker while it was still in contact with a force on it, there would be acceleration from the force. The marker moved strictly horizontally. We only measured the point mass in the horizontal direction, this way that we wouldn't get any varying points in the y direction. There was a large change in x, it was around 0.6 of a meter, and the camera should remain stationary throughout filming for no added change from the frame of reference. In the experiment itself, we chose to do a marker rolling across a whiteboard, as the whiteboard would have less friction than that of the floor. We filmed the marker from above and made the system, and while my partner rolled the marker across the whiteboard horizontally, everything else was the surroundings. All other surroundings, such as the friction of the air on the whiteboard, were hoped to be ignored. Here is the model from the GlowScript. It shows that the red line is the GlowScript model and the blue line is the tracker model, where the light blue line is the trend line from the tracker, because it was actually found to be some acceleration here in the form of friction. However, the trend line is shown to have an r-squared value of 0.992, which is close enough to 1 that it is assumed that all points on the actual line have a very small variance and can be considered as the true velocity. And the true velocity from this trend line is 0.379, and the true velocity from the GlowScript is 0.376, so a very small discrepancy between those two. Here is the actual code for my GlowScript. Here's from the start to the finish. You can see that the velocity is here. It's a little bit more specific than it is on the model. The change in delta t is very specific as well as the time for the thing to go on. You can see, however, that this t is very large. This will come up later. Excuse me. Here we go. Similarities and differences. The graphs are different because of the acceleration. Otherwise, the acceleration is pretty negligible because of the r-squared value. The slope is almost the same, so velocity should be about the same, and there is no or low acceleration, which means that there is almost 0 net force. Overall, there's very minimal differences. Reasoning, displacement versus time was done to show that since if the slope of this was consistent, then the velocity would be consistent as well, since the velocity is the slope of displacement versus time. The incline on the whiteboard needed to be perfectly horizontal, or else the marker would have an additional acceleration. And since r-squared is so close to 1, and the beginning and the endpoints are equivalent, it is safe to presume for the sake of the lab that acceleration due to friction is negligible. Here are some of the errors. The velocity of GlowScript was found by the final exposition minus the initial exposition divided by the total time. It's found to be this very specific number, whereas the velocity was found from the trend line of the slope of the tracker, and is 0.379. So overall, there's a small error of less than 0.003 meters per second. R-squared did not exactly equal 1, and so therefore friction was present, but it was very close to 1, so it was negligible. And then there was some camera shake as the video took place, which added onto and expounded upon some of the prior errors. However, though, there were minimal physics errors. Sources of the errors: since there were only 9 data points instead of 98, the trend line is likely off within the tracker model. For some reason, the tracker model change in time wasn't consistent, and therefore I couldn't use all of the time points that I found in my GlowScript model. The longer video also made the friction much more apparent. If I was to do this again, I would have a much shorter video. And additionally, some of the human errors on the tracker point mass probably were present, and the camera shake was also present. Overall, shorter video with more data points. Some of the what-if questions asked, what if the axis was flipped? Then the velocity would be negative with the same magnitude. Since we're ignoring the friction, the only two forces acting on the system are the normal force and the force of gravity, which are equal and opposite and cancel out. Here's my video in case you wanted to see.